Hello friends, in today's data structure class, we will see the next topic from first unit, that is introduction to data structure, is asymptotic analysis, that is analyzing the runtime of algorithms by using asymptotic notations. Here there are three different notations: big O notation, big omega notation and theta notation. Let us see all those things in detail our class. Analyzing runtime of the algorithm means how much time the algorithm will take to complete its execution. That is, the speed of an algorithm can be analyzed by using execution time of its statements and loop. Okay, statements will take a constant time, but when come to loop, the loop can be counted the number of iterations it takes to a function to complete. Okay, so based on the number of times the loop will get executed, accordingly, the execution time will get changed. Right. So based on the input size n, the performance will get changed. Suppose if the input size is less, then the number of iterations in the loop will be very less. Suppose if the input size is very large, n equal to very large number, then the number of iterations in the loop will get very much increased. So this will directly affect the efficiency of algorithm. That is, the efficiency of an algorithm depends on amount of time, storage, and other resources which are required to execute the algorithm, and it is measured by using asymptotic notations. Okay, so based on the number of input size and based on the storage and other resources required to execute this algorithm, the efficiency will get changed, right? This efficiency is categorized into best case, worst case, and average case. Okay, what is best case? Let us take bubble sort as example because this is the simplest sorting algorithm. In this sorting algorithm, we have to give the unsorted array elements. Okay, that is some random numbers will be given to the algorithm, bubble sort algorithm. Then we will get the sorted array in ascending order as output. Okay, this is input. Unsorted array is input and output will be the sorted ascending array. So this is bubble sort. Okay, let us take this bubble sort as example. If the input is already sorted, suppose if we give input as already sorted array, that is 1, 2, 3, 4, accordingly we can give input to the bubble sort, then the output time, how much time it will take to sort these numbers, the time is linear because very less time these values will get sorted. So this is called as best case or best time. Okay, because the array is already sorted, hence it will take very less time to sort the array, right? Let us take the another case, that is case 2. Here, suppose if we give the reverse condition, that means the input is 4, 3, 2, 1 in the reverse order. Okay, now we need to uh, sort these particular items. What will be the output? 1, 2, 3, 4, right? So for this, it will take maximum time. It will take maximum time because the input is reverse order. The output should be ascending order, right? So for reversing the entire thing, the algorithm will take maximum time. The time is quadratic, okay, to sort the element, and this time is called as worst time because it will take maximum time to sort the array. Okay, and the last one is case 3. Here the input is neither sorted nor in reverse order. Okay, some random number. For example, the original array. Okay, 2, 1, 4, 3. Now it will take average time to sort the array. The algorithm will take average time to sort the array. Okay, these durations, how many time it will take to sort the array, these durations are denoted by using asymptotic notations. Okay, The asymptotic notations are mathematical notations which are used to describe the runtime of an algorithm and to identify the class of function. Okay, which class the function will belongs to, either best case, worst case, or average case. Okay, so in any algorithm, the time complexity of your function should be any one of the below value. The least value is 1 and the last value is n power n. Here n is nothing but the size of input size. N is nothing but input size. So based on the input size, the efficiency will get changed and the time complexity, that is the time taken to complete the algorithm, will lies any one of these values. Okay, based on this value, we can identify the notation or class of the function. Okay, the values are n, log n, root n, simply n, that is linear n log n square, n cube, etc. 2 power n, 3 power n, etc. up to n power n. Okay, so this is the least value and this is the last value, right? So there are three asymptotic notations. First one is big O notation, big omega notation, and theta notation. Let us see these things in detail. So first, let us see the big O notation. Okay, it is represented by capital O. It represents upper bound of the runtime of algorithm, runtime of the function. Okay, let us start from n0, n0, the algorithm. If the algorithm input got increased, this is in n size. Okay, if n size got increased, then the performance will get increased. Here we are having two functions, f of n and c g of n, right? So f of n is uh, the expected function, expected value, and g of n is the measured value. Okay, hence the measured or the computed g of n should be always above the expected or theoretical value. Okay, the calculated value should be above the theoretical value. Then this will come under big O notation. That is the upper bound. That means the value should always lies any of this region. Okay, the function f of n, which is equal to O of g of n, if and only if there exists positive constant n0 and c. Okay, this is n0 and c may be anywhere in this region, such that f of n is less than or equal to c into g of n for all n is greater than n0. For all n is greater than n0. For all n in this input value. Okay. Hence, f of n is any value of these value. Any value. So we will get any of these values, because already we have seen the runtime efficiency of the algorithm will lies any of these values, isn't it? Now, if it is big O, that is upper bound of runtime, then the value should be anywhere here, right? Here, which is the closest one, closest to n, isn't it? So f of n equal to O of n is most close value. Okay, f of n equal to O of n is the most close value. We can take like that. So O of n, that should always above the n value in this region. The next notation is omega notation. This is exactly opposite to big O notation. Okay, here the omega notation represent the lower bound of runtime of an algorithm. That means that lies anywhere in this region. right? F of n is the expected and G of n is the computed. G of n is the computed, okay? So the computed value should always lies below the expected value, then that should be represented by using omega notation. Okay, here the function f of n equal to omega g of n if and only if there exists a positive constant 0, n0, this is n0, and c is any of the random value such that f of n should be less than or equal to c into g of n. So f of n is greater here. Okay, f of n value is greater when compared to c into g of n for all n greater than or equal to n0. So n is input. Okay, hence the f of n value should be any one of these value. Okay, 1 log n root n. Okay, so this is the value of runtime of an algorithm. Here the omega value should come in this region, any one of these region, and here the most close value is n. So f of n equal to omega of n is the most close value. So this is the omega notation. The third notation is theta notation. Here the theta notation encloses the function above and below. Okay, see here the g of n value lies between this region. Okay, this is C1 and this is C2. That is, this is lower bound and this is upper bound. Here the theta notation will lies anywhere here. Right? It represents the upper and lower bound of runtime of the algorithm. It uses the average case complexity of an algorithm. It is used to compute average case complexity of an algorithm. Okay, let us see the function. So the function f of n equal to theta g of n if and only if there exists positive constant c1, c2 and n0. C1 may be anywhere else here lower side, C2 may be anywhere else here upper side, and N0 is here. That is the starting. Okay, such that 0 greater than or equal to C1 G1. C1 G1. So that should be greater than here, and that should be greater than or equal to f of n. This is f of n, and that should be greater than or equal to C2 G of n. C2 G of n is here for r n greater than n0. N is input. N is input. Okay. Hence, this efficiency value of this algorithm may be lies any of these value. Any of these value. It may be less than here or it may be greater than here. Okay. Hence, the most close value is here. Total number of input. Okay. So this is theta notation. Algorithm complexity. Where calculating the algorithm complexity, the time and space are two main factors which determines the efficiency of algorithm. Okay. The complexity of algorithm is f of n, which provides the runtime or the storage space needed by the algorithm with respect to n number of inputs. If input size increased, then the time and storage space will also be increased for completing this algorithm. If it is less, then the algorithm will be completed very fast with less time and minimum storage space, right? Now, the time factor. What is time factor? It is calculated by counting the number of key operations such as comparisons, number of comparisons in the sorting algorithm. How many times we are going to compare the numbers to sort the array, right? So this is time factor. And space factor is measured by the counting the maximum memory space. How many variables are there in a loop? Okay. So maximum memory space required by the algorithm. Okay, so the time factor and space factor are very important, and those are computed by using the algorithm complexity, that is f of n. And first let us see the space complexity. The space complexity of an algorithm represents the amount of memory space required for the algorithm in its life cycle. Okay, how much memory it requires to execute the algorithm is calculated by using space complexity. It is the sum of fixed part plus variable part. What is fixed part? It is a space required to store certain data and variables. Okay, that is the simple variable and constant based on and the program size, which are not dependent on the size of the input or size of the problem. Okay, so this is fixed part. And what is variable part? This is the space required by the variable whose size is totally dependent on size of the input. That is, during runtime, this variable part size will get changed. For example, dynamic memory allocation. So during runtime only, we came to know that how much size will be required for this variable part. Hence, the space complexity of a program P, that is S of P, which is equal to A plus SP of L. A is fixed part and this is special part, that is variable part. For example, let us take this statement R equal to sum of P comma Q plus 10. Here we have to add this P and Q plus the constant 10 that should be stored in the variable R. So what's the algorithm here? Start and R equal to P plus Q plus 10 and stop. So in this algorithm, which are the variables? P, Q, R are variables. See, P, Q, R are variables. And we have one constant 10. One constant. Hence, the space required is 1 plus 3 or 3 plus 1. Okay, which is equal to 4. Okay, and this 4 is depending on the data type of the given variable. Okay, for example, if P, Q, R are integer type, then the space required for this algorithm is 4 into 2 because 2 bytes is the size of integer, right? So 8 bytes. If it is float, accordingly we need to multiply that value. Okay. The next one is time complexity, which is used to represent the amount of time required to execute an algorithm. Okay. Now let us take T of n. T of n is the steps in the algorithm, that is number of steps in the algorithm, and each step takes a constant time. Okay. Let us see one example for this. Addition of two n-bit integers. Addition of two n-bit integers which requires n steps. For example, let us add 1, 2, 3, 3, 1, 4. Okay, these two n-bit integers, 3-bit integers, two 3-bit integers we are going to add. Okay, first we have to add the first bit. This is 7, and let us add the second bit. This is 3, and this is the third bit. This is 4. Okay, so it requires n steps. Suppose if the digit is 3, then it requires 3 steps. The total computational time is T of n, which is equal to C into n. What is C? C is nothing but the time consumed for add of 2 bits. So this is 1 bit, this is another bit. So how much time it will take to add these 2 bits? Okay, so how much time it will take? 2 into 3. 2 into 3, okay, 6. So the T of n grows linearly as the input size increase. Suppose if we add 4 or 5 size input, 0, 5. Likewise, if we increase the number of digits, accordingly, the time will also get increased. The time complexity of a function should be any one of the following values. As we already see, that will come under any of these values. And these are different types of time complexity, starting from the constant 1 to worst case n power n. Okay, so this is constant and this is logarithmic O of log n, this one, and this is linear, this one, and log linear. Okay, this is n log, and this is O of n square, and this is quadratic. Okay, this is quadratic. After that, this is exponential, 2 power n, 3 power n, and finally this is the worst case. Okay, so these are different types of time complexity values with respect to input size and computation. So far we have seen the 3 different asymptotic notations, that is the big O notation, omega notation and theta notation. After that, something about the time and space complexities. In the next class we will see another important topic from first unit. Thank you.